Welcome back to Chapter 17 of Physics. We've previously gone over electric potential, capacitance, and current and resistance. In this final segment, I'll be talking about electric power. There are two common sources of current that are used for electric power. The first are batteries, which convert chemical energy to electrical energy through a chemical reaction that takes place within the battery. The second type is a generator, which converts mechanical energy to electrical energy. An example of this would be a generator that incorporates falling water in a hydroelectric power plant. This essentially means that the gravitational potential of the water converts to mechanical energy, which is used to generate electricity. There are also two different types of current. Direct current moves in one direction over time, so essentially the charge has a net velocity and net displacement because it's always moving in the same direction. Conversely, alternating current means that the direction of the current is always changing, so this motion could be seen more as vibrating back and forth rather than net motion in a certain direction. So I've drawn this below with these two graphs. Electric power is similar to the standard power that we've learned about previously, in that it's the rate of conversion of electrical energy. So we write power as work divided by time, or change in potential energy divided by time. We also know that potential difference is equal to change in potential energy divided by the charge. So we can multiply this Q over to the other side to isolate the change in potential energy, which we'll call delta V times Q. Now, as you can see, we have this expression for delta P, which can plug into the top. So we get that the power is equal to delta V times Q over T. Finally, we know that Q over T is the rate of charge transfer over time, which is the current flow. So we can simplify to write that electric power is equal to I, or current, times delta V. That's the expression for electric power. And the units for this power, like typical power, is the watt. However, there are also kWh, or kilowatt hours, which is how electrical companies usually measure electricity use. Here are some practice problems. Number 1. A 1050 watt toaster operates on a household circuit of 120 volts. What is the resistance of the wire that makes up the heating element of the toaster? So we'll use the equation from the last slide, where we learned that power is equal to I, or current, times delta V, or potential difference. We know that the power is 1050 watts. We're solving for the current, or I, and then finally the potential difference in volts is 120. Now to isolate I, we'll divide both sides by 120 to get that the current is equal to about 8.75. Now we're not completely done because they're asking for the resistance. So we'll have to turn to another equation that we've learned, where V is equal to IR. Now we know the potential difference, which is 120 volts. We know the current, which is 8.75, and we're solving for the resistance in ohms. By dividing both sides by 8.75, we get that the resistance, or R, is equal to about 13.7 ohms. Number 2. A calculator is rated at 0.1 watts and has an internal resistance of 22 ohms. What battery potential difference is required for this device? So again, we'll be using two equations to solve this problem. We have our first one where P is equal to I times delta V. We also know that since V is equal to IR, to isolate I, we would get that I is equal to delta V over R. Now we're ready to solve. We can plug in this I over on this side to find that power, or P, is equal to the quantity delta V squared divided by R, which is resistance. We know that the power is 0.1 watts. We're solving for delta V, which again is squared on the top, and then divided by resistance, which is 22. If we multiply this 22 to the other side, we get that 2.2 is equal to delta V squared. We can take the square root of both sides to find that delta V equals 1.5 volts. This has been Chapter 17 of Holt Physics, where we've looked at electrical energy and current. I'm Annika, and thank you for watching.